Okay, good morning, everyone. So today we will continue our discussion and our exploration about action and action approach to E&M fields. Okay. So in the last couple lectures, we learned an important principle and the practice. Okay. So that is, if we know the symmetry of the system, we can almost uniquely write down the action. Okay, in most cases. And the only thing we will not know, we cannot determine by just looking at the symmetry, is the number of the coefficients. But as we showed in lecture and in your homeworks in last week, the symmetry already fixed the structure of the action. And they tell us how many unknown parameters we need to measure experimentally. Okay, so this is a very important physics principle, and it is also very useful. So it tells us, even if we don't know anything about the system, as long as we just roughly understand the symmetry, we can write down the action. And once we write down the action, we can write down all the physics laws, like the equation of motion, etc. Okay. So in the last week, we demonstrated this for E&M field in our lecture. And we also looked at the motion of charged particles, relatively charged particles in our lecture. And in our homework, we showed that the same principle actually works much more generically. It not only works for classical mechanics like waves, it actually also gives us a Schrodinger equation of quantum mechanics. Schrodinger equation, I'll say the Dirac equation in quantum mechanics, can be described in the same approach. Okay. So today we will continue. This week we will continue our exploration about the important role of symmetry. Okay. And in the next few lectures, we will explore another very important physics associated with symmetry. That is a relation between symmetry and the conservation law, also known as the noise theorem. Okay? So noise theorem tells us for every continuous symmetry, there will be a corresponding conservation law. In other words, as long as we can find continuous symmetry in our system, we will be able to define a quantity, and that quantity is a conserved quantity. You cannot create more. You cannot destroy that quantity. As long as we have one system, that's the number of that quantity always remains the same. Okay, so that is noise theorem, and this is another very important application of symmetry. Okay, so basically, symmetry gives us two things. One is symmetry tells us what does the action look like. Okay, it's almost uniquely determine the structure of the action, except for the number of control parameters, the number of those coefficients. Okay. And the second, if we know the symmetry, we will be able to figure out how many conserved quantities we have in our system. And as we will show later in this week, this noise theorem gives us direct definition of charge, energy, and momentum, etc. So the typical conservation law or conservation quantity we discuss in physics can all be obtained from this approach. Okay, so that is what we are going to look at. Okay, so let's start by explaining a little bit about these sentences. Okay, so this sentence actually contains two words, and it basically says two words are equivalent to each other. One word is continuous symmetry. Okay, another word is a conservation law. So let's start from the second one. Start from the conservation law. What is a conservation law? Okay, as we learned in undergraduate courses, conservation law means there is some quantity, and its value cannot change. Okay, so for example, energy. We cannot create energy. We cannot destroy energy. We can only move energy from one area to another, one region to another region, or transform energy from one form to another form, but the total amount of energy cannot change. Okay, that is conservation law. But in field theory, as we discussed earlier on, conservation law itself should be combined with the principle of locality. Okay, if we combine conservation law and the principle of locality together, we get a continuity equation. Okay, so in field theory, typically the conservation law appears in the form of a continuity equation. The continuity equation, for example, this is the continuity equation of charge we have earlier. Okay, so the first term tells me charge density at the local at this point is changing. Okay, time derivative means how fast it's changing, and the second term tells us this changing of charge density is not coming from nowhere. Okay, the only way we change this charge density and this local region is through some current. Okay. And if we take an integral on both sides, the left-hand side will be the charge in a region. And the second term will gives you a surface term from Stokes' theorem. The surface term tells you the current that goes through the surface of the region and go into the system or go out of the system. Okay, so basically continuity equation tells us for any region, the total amount of charge inside this region must match the amount of charge that goes through the boundary. Okay? If we have more charge, it means there are more charge, more current that goes through the boundary coming into the system. If we have less and less charge as we increase time, then it means charge is flowing out. Okay, so the conservation law in physics in continuous system in field theory always appears in the form of a continuity equation. Okay? So the continuity equation is conservation law, and conservation law is continuity equation. Of course, the hidden assumption here is we follow the principle of locality. Okay? As we explained earlier on, principle of locality tells us charge cannot teleport from one point to another. Charge can only flow from one point to another. Okay? If charge can only flow from one point to another, then if we want to change the value of charge in this region, the only way is to have a current go through the surface of this area. That is the second term. Okay? So continuity equation describes conservation law, and it also obeys the principle of locality. Okay? Bottom line, for the continuous system, conservation law is continuity equation. Continuity equation is conservation law. Okay, so the second part here for field theory or for continuum systems, Noether theorem, the conservation law here means we can write down a continuity equation. Okay, and the first part of Noether theorem talks about continuous symmetry. So what is a continuous symmetry? Okay. So before we answer that question, let's first look at a broader definition of what is symmetry. Okay. Symmetry in physics means that we can do something to the system and the system remains the same. That is called symmetry. Okay. For example, what we call the translational symmetry. Okay. We know for the translational symmetry, it means that we can translate our space and all our physics laws and all our physics, our universe and our physics laws should stay the same. Okay. Which means if I do my experiment here in this region, I get a physics law, say Newton's equation. Okay. And then I repeat the same experiment somewhere far away, okay, say on the moon. And I do the same experiment and I find the same physics law, which is also Newton's equation. Okay. Translational symmetry means here and there, system is the same. In other words, if I move my system from here to there, everything remains the same. Okay. So symmetry in physics means if we do something, the system does not change. That is called symmetry. Okay. And symmetry, and on the mathematical side, we can make a more rigorous definition of symmetry by looking at the action. Okay, as we explained early on in last week, mathematically we can define symmetry as the action remains invariant under certain transformation. Okay, because action defines as equation of motion, action defines as physics laws. So if action stay the same before and after the transformation, then I know my physics laws stay the same before and after my transformation. So that is a more mathematical way, more mathematically rigorous way to define symmetry. Okay, and there is a small note here. Okay, so although in our lecture we will say that symmetry means action stay invariant. Okay, so there are two special cases where this is not true. These two special cases, one is known as spontaneous symmetry breaking. Okay, so spontaneous symmetry breaking means action. It looks like it has some symmetry, but this symmetry is spontaneously broken by the ground state. For example, what we learned in statistics physics, like the Ising model. The Ising model itself, spin pointing up and pointing down are fully equivalent to each other. But if we cool down system to very low temperature, we will find that spinlets themselves will choose one ground state, either all spin up or all spin down. If the spin chooses the all spin up ground state, up and down is no longer equivalent, although the action or Hamiltonian has this symmetry, but the system itself don't have this symmetry. That is known as spontaneous symmetry breaking. Okay. Another exception for this definition of symmetry, the action stay invariant under certain transformation, is known as anomaly, or more precisely known as gauge anomaly. Okay. So that situation is the gauge anomaly is a little bit more exotic. That is actually interacting It is actually because of the quantum fluctuation and the interactions between gauge field. Okay, so because of quantum fluctuation and the interactions between gauge field, although the action you write down looks like there is a symmetry, it stays invariant under certain transformation, the system itself actually does not have that symmetry due to a so-called gauge anomaly. Okay? But these two physics, spontaneous symmetry breaking and gauge anomaly, is not something we're going to explore in this course. Okay, so in this course, we will ignore these two special cases. When these two special cases is ignored, then symmetry means action stay the same under some transformation. Okay, so that is our definition of symmetry in physics most of the time, except for spontaneous symmetry breaking and gauge anomaly. Okay, so nevertheless, let's don't worry about spontaneous symmetry breaking and gauge anomaly here. So we define symmetry as action remains invariant under certain transformation. Okay, so that is the symmetry. And what is the continuous symmetry? Continuous symmetry means this transformation we use to define the symmetry can be done in a smooth and continuous way. Okay, which means it can be done gradually and smoothly. Okay, so for example, translation, space translation. This is the so-called continuous symmetry. Okay, so for example, if we want to do a translation by say 1 meter, I can do this 1 meter translation smoothly and gradually. Okay, I can first do a 0.1 meter, then another 0.1 meter, another 0.1 meter, another 0.1 meter. Okay, I can do a small transformation and use this small transformation to build this big transformation. Okay, and this small transformation can be very, very, very small. Okay, I can do a 0.1 meter translation. I can do a 0.01 meter translation. I can do a 1 answer translation. So you know, in other words, there's no lower bound for my transformation. I can do a so-called infinitesimal transformation. So this transformation is actually the smooth one. Okay, and this distance, the distance of my translation, is a smooth and continuous variable. Okay, so that is called a continuous symmetry. And opposite to continuous symmetry is what we call discrete symmetry. An example of discrete symmetry is like mirror. Okay, if we take a mirror image of something and this object stays the same, that is called a mirror symmetry. And this mirror transformation is not a continuous transformation because you cannot do a mirror image gradually. Okay? The mirror image is like jump from original picture, jump to the final picture. There's no way to gradually change something into its mirror image. Okay? Another example is time reversal, flip the direction of time. Okay, so flip the direction of time means time going to the positive direction or negative direction. Plus or minus, this is a discretized flip. It's not something you can gradually flip. Okay, so like translation and say rotation, those type of operations are known as a continuous transformation. Okay, so for example, rotation, I can rotate my system gradually to my targeted position. Okay, I don't need to jump to it. But for like space inversion or time reversal, those transformation is discretized. It's discrete. Okay, it's a jump. Okay. So if the transformation we use to define the symmetry is continuous, we call it a continuous symmetry. If the transformation we use to define this symmetry is discretized, then we call it a discrete symmetry. Okay. So continuous symmetry includes such as space translation, space rotation, and Lorentz boost. Lorentz boost is also a continuous symmetry. The Lorentz boost, the control parameters there is velocity, is the relative velocity between two reference frames. And that relative velocity can be very, very small. Okay? That velocity is a continuous variable. Okay? So Lorentz boost is also a continuous symmetry. And discretized symmetry are such as mirror image, space inversion, time reversal, or particle Hall transformation, for example. If we change particles with antiparticles and antiparticles to particles, this transformation is a discretized one. It cannot be done gradually. Okay. Okay, and also the icing symmetry we learned in statistics physics, flip spin from up to down. That is a discretized symmetry. Okay. If you gradually rotate it from up to down, this gradual rotation is a continuous symmetry. But if you just suddenly flip it from up to down, that is a discretized symmetry, a discrete symmetry. Okay. And mathematically, continuous symmetry or this continuous deformation is also known as differentiable. Okay. Differentiable is a mathematical terminology to describe how continuous this function is. Okay. And so for us, usually we say something is smooth and continuous. For mathematicians, the smooth and continuous actually need to be rigorously defined. And usually that is defined through differentiable. And usually what we call the continuous means it's infinitely differentiable by mathematicians. That's the mathematicians terminology for the same thing. Okay, nevertheless, now we know the definition of continuous symmetry. And we also know that the corresponding conservation law means a continuity equation. Some forms of continuity equation. And then the noise theorem actually tells us any continuous symmetry will give us one continuity equation. That is what this theorem is. Okay. So to get a better understanding about this theorem, let's look at one example. Okay. So this example, the first example we are going to look at is the so-called gauge symmetry. And the gauge symmetry will give us charge conservation. Okay. So what is the gauge symmetry? The gauge symmetry is a symmetry defined by gauge transformation. Okay. So in earlier lectures, we know that we can use E and B field to describe electromagnetics. Okay. And we also explained to you that E and B field are sometimes not the best option. For example, if you want to do action, you want to do vibration principle, it's much better to use scalar and vector potential, phi and A, to describe your E and B instead of E and B, okay? Because they don't have constraint, as we explained earlier. And we also mentioned in early lectures, if we use scalar and the vector potential to define E and B, this scalar and the vector potential are not uniquely defined, okay? For the same E and B field, I can choose to use phi and A to describe it, or I can choose to use phi prime and A prime to describe it. As long as phi prime and phi A prime and A are related by this relation, so-called gauge transformation, phi and A, phi prime and A prime, they describe the same E and B. Okay, I can use this guy to describe my E and B field, and if I add a time derivative of some function lambda and the spatial derivative of some function lambda to the scalar and the vector potential, and get the new scalar and the vector potential. This new scalar and the new vector potential actually gives me exactly the same E and B. Okay, so we can use phi and A or phi prime and A prime. They describe the same physics. This transformation is known as a gauge transformation. So gauge transformation transforms me from one set of phi and A to another set of phi prime and A prime. Okay? So these two sets of phi and A, phi prime and A prime, they describe the same E and B. So nothing actually changes if I choose to transform phi and A to phi prime and A prime. In other words, if I do my gauge transformation, nothing should change in my system. They are describing exactly the same E and B field. Okay, because nothing will change in my system under this transformation. This transformation should be a symmetry. It's a symmetry, and this symmetry is the so-called gauge symmetry. Okay, and we utilize this gauge symmetry early on when we try to write down the action. When we try to write down the action, we mentioned that the action have to obey this symmetry. The action must stay invariant. If I change phi to phi prime and change A to A prime, action must stay invariant. Okay. Oh, and by the way, this is a four-dimensional version, 4D vector version of the gauge transformation, which we also discussed earlier. Okay. So the bottom line, gauge symmetry means for my action, okay, it should stay invariant if I change phi to phi prime and A to A prime, and phi and A is defined this way. Okay. So that is a gauge symmetry. So that's the definition of the gauge symmetry. And this gauge symmetry is a continuous symmetry because this transformation is defined by lambda. And the lambda is a real function. And the real numbers are continuous numbers. Okay, this lambda can be very small and can be very big. I can do a small transformation for the lambda is very small, and I can use a bunch of small lambda to add them together to get a big transformation. Okay, so this is a continuous transformation because lambda is a continuous and smooth function. Okay, and since this is a continuous symmetry, it should define for us conservation. And what is that conservation? Okay, so let's look at this symmetry and utilize this symmetry to define the conservation. Okay, so first of all, this is my action. Okay, my action has E and M field, and coupling between E and M field and the matter, and also the action of the matter. Okay, as we showed in the last week's lectures. And now let me perform this gauge transformation. Okay, so in this gauge transformation, I will replace phi by phi prime, A by A prime, and now I get a new action. Okay, so this new action is action after the gauge transformation. And it's the same action, but I replace phi with phi prime, a with a prime. And the gauge symmetry tells me my new my new action S prime and S must be exactly the same. Okay. Nothing should change if I perform this transformation. So that is my symmetry. So I want to argue that the symmetry, if I request S prime and S are the same, this so-called gauge symmetry, then I can get the conservation. Okay. That is what I'm going to prove. So first of all, let's look at the matter part. Okay. The matter part describes the motion of my matter, my particle. Okay. And those matter parts does not contain E and B field. It does not contain phi or A. Because the matter part doesn't contain phi and A. Under gauge transformation, matter part cannot change. Okay. The only thing I change here is I change phi to phi prime, A to A prime. If the matter part does not depend on phi and A at all, then the matter part does not change. Okay. So the matter part, S prime and S equal to each other automatically. We don't need to worry about that. What we need to look at is the first two terms. Okay? The first two terms, indeed, they depend on phi and A. So we need to ask, how do they change under the gauge transformation? And how can we make sure that they don't change under the gauge transformation? Okay. And now let's first look at so the matter part is okay, it's taken care of automatically. Now let's look at the first term, the E and M part first. The E and M part is this guy, E squared minus B squared, as we explained, as we learned earlier. Okay? This term is automatically gauge invariant. Okay? Gauge invariant means this term does not change under gauge transformation. Okay? The reason is, as we explained earlier, gauge transformation changes phi and A, changes the value of phi and A. But phi and A and phi prime and A prime gives you the same E and B. Okay? E and B are derivative of phi and A. And as we proved earlier, gauge transformation changes the value of my scalar and vector potential, but it does not change the field strength E and B. That's the point of gauge transformation. Okay? It changes the potential, but it does not change the field strength. So under gauge transformation, E and B doesn't change. And thus the new action, E and M part, stays exactly the same. Gauge transformation do not change E, do not change B, but do not change E squared minus B squared. The first term of my action automatically tells me it's the invariant under gauge transformation. Okay? Gauge transformation does not change this part. And it does not change the matter part either. The only part we need to look at is the coupling part. Okay? That's the part we need to look at. The coupling part does depend on phi, does depend on A. Okay? So this is the coupling part before gauge transformation, my old action. Now let me do the gauge transformation. Okay? Gauge transformation means now I get a new action. The new action is almost the same as the old one. I replace phi with phi prime. Okay? And I replace A with A prime. And I get a new action. This action is what I call S prime. Okay? And what is phi prime? Phi prime is a gauge transformation of phi. It's this guy. Okay? That's the definition. A prime is the gauge transformation of A. Okay? And that is defined up here. This is phi prime, this is A prime. Let's plug in the definition of phi prime and plug in the definition of A prime. Okay. Now I have two terms here, two terms here, four terms altogether. Okay. Let me regroup these four terms a little bit. I have a phi times rho term. I put it here. Okay. I have a j times A term. The j times A term, I will put it here. Okay. And the rest two terms, rho times derivative of lambda, I put it here. J times derivative of lambda, I'll put it here. Okay. And I'll also be careful so that the sign stay correctly. Okay. Oh, by the way, there is overall minus sign in front for the definition of the action. So that minus sign cancels some of the minus sign. So at the end of the day, this term has a minus sign, the second term has a plus sign. You can verify that. Okay. Nevertheless, I regrouped these four terms, the two terms here, the rest two terms here. Okay. And let's look at the first part first. Okay. What is this? This guy, by definition, is my old action before gauge transformation. Okay. So the first term is S without prime. So S prime equals to the first term, S without prime, plus this term, plus this term. So I can rewrite my new action S prime as my old action S plus one additional term. And gauge symmetry tells me action, new action S prime and old action S should be the same. They should be equal to each other. Okay. If I want to make sure that these two terms are equal to each other, then it means this additional term must be 0. Okay. So gauge symmetry tells us this additional term must be 0. That's the only way to make sure that action stays invariant under gauge transformation. And what does this term equal 0? Okay. Let's look at this term a little bit more. First of all, let's perform a so-called integral by parts. Okay, so let me write this down quickly. So if we have f function f x times d dx gx integral dx, okay, we know that this guy equals to minus dx df dx times gx plus some boundary term or surface term. bt means boundary term. It only appears on the boundary. Okay. So integral by parts means if I have a integral of two functions, one function has a derivative, I can move this derivative to the other function. I can move this derivative from g to f, and that gives me minus sign and some boundary term. Okay. The boundary term are not important. Okay. If we have an infinitely large system, the boundary doesn't matter. So boundary term we can drop. If we drop the boundary, basically integral by part means I can move this integral from lambda to rho, and I get a minus sign. So that's what we get here. Okay. Integral by part, move partial t to rho, and minus sign. Similarly, I move the spatial derivative from lambda to j, and get a minus sign. Okay. Now my derivative goes to j and rho. Lambda don't have derivative anymore. There's no derivative for lambda. I can pull this common factor lambda out. I can pull this common factor lambda out, and this is what I get. And my gauge symmetry tells me this object needs to be 0 for any lambda, for any gauge transformation, for any lambda, this needs to be 0. Okay. If this guy is 0 for any lambda, then that means this guy has to be 0. Okay. And this guy has to be 0 is nothing but my charge conservation law and continuity equation for charge. Okay. It tells me if I want to change charge, the only way to do that is to sending in the charge, sending some current and make this current go through the surface. That is how you change the charge inside the system. So that is the continuity equation. Okay. So here we demonstrated that gauge symmetry, the so-called gauge symmetry, everything stays the same, no matter which gauge choice we use, implies immediately a continuity equation. And this is a conservation law. And this is one example of noise theory. Okay, symmetry, a continuous symmetry, gives us a conservation law. Okay, so let me erase everything. Okay, so a couple comments associated with this continuity equation and charge conservation law. Okay, so in E&M, we will say the charge conservation law comes from the gauge symmetry. It's a consequence of the gauge symmetry. In quantum mechanics, you probably learn a different statement. In quantum mechanics, we say the charge conservation law comes from the U1 phase symmetry of the quantum wave functions. Okay, what does that mean? The U1 phase symmetry means I have a wave function per psi. Okay, I can change the complex phase of this per psi, multiply this wave function with a complex phase e to the I5. And now I get a new wave function per psi prime. In quantum mechanics, per psi prime and per psi describe exactly the same physics. Nothing changes if I flip per psi to per psi prime by just changing the complex phase. Okay. That symmetry, that is again a symmetry. Nothing changes under the transformation. That symmetry in quantum mechanics is called the U1 phase symmetry. And in quantum mechanics, we say that the U1 phase symmetry is the reason of charge conservation. Okay, so in two different courses, we have the same charge conservation law, but we give two different reasons. Gauge transformation in E&M, gauge symmetry in E&M, U1 phase symmetry in quantum mechanics. Okay, and these two statements and these two symmetry are actually not conflict with each other. They're actually exactly the same thing. As we briefly mentioned in one of the earlier lectures, okay, the full structure of gauge transformation is this. Okay. In E&M, we show that gauge transformation changes scalar potential, and it changes the vector potential. But if you want the full gauge transformation, in the same time, you need to change the complex quantum wave function by a phase. And that phase is exactly the same lambda we use here. Of course, divided by a Planck constant h bar and multiplied by charge of this particle. Okay, multiplied and divided by some physics constant. So up to some physics constant, change the complex phase of wave function. And gauge transformation in E and M are exactly the same thing. They are the same transformation, and they are the same symmetry. Okay, so in quantum mechanics, we emphasize this part. In E and M, we emphasize this part. But in reality, they are related. They are the same transformation. And the charge conservation actually comes from this transformation, this whole transformation, okay? This whole thing. Just in E and M, we call it gauge transformation, gauge symmetry. And in quantum mechanics, we call it U1 phase symmetry. They're actually the same thing. Okay, that's the first comment I want to provide. And secondly, you probably remember in the proof here, I utilize integral by parts, and I argued that the boundary term doesn't matter. Okay, and the exact reason the boundary term doesn't matter, actually there is an exact argument here. Okay, so the reason that boundary term doesn't matter is we argue in our system there is no charge on the boundary, and there is no current on the boundary. Okay, if there is no charge on the boundary and no current on the boundary, then the boundary term of course is zero because there's nothing there. Okay, if this is true, the boundary term automatically disappears. Okay, so we'll assume in our system there's no charge and there's no current on the boundary of our system. What if there is charge or there is current on the boundary of our system? What if there is current or some charge on the boundary of our system? Then what we can do is we choose a larger area. Okay? We enlarge our system. We make a larger area. And this larger area would enclose this current. And if we choose this larger area, those current is no longer a boundary current. It's a bulk current. It doesn't give us boundary contribution. Okay? We choose a larger area such that my charge and current are both, sorry, it's equal to zero, not equal to zero. Charge and current are both zero. Okay, we choose a larger area. Make sure that charge and current are both zero at the boundary. Okay? If a larger area still has some charge or current at the boundary, then we choose an even larger area. Eventually we choose the entire universe, and hopefully at the boundary of our universe, there is no charge or current. Okay? If at the boundary of our universe, there is some current, say, flowing in, then it means that probably is not the boundary of our universe, okay? Because there are current flowing in or out. Then it means there is something on the other side. We probably should choose another larger area to call it our universe, okay? So in any case, we can always choose area to be larger and larger and larger. Eventually, the boundary has no charge and no current. Rho equals zero, J equals zero at the boundary. And that is the real reason why we can usually throw away the boundary term in this integral by parts procedure. Okay, so that is actually one very important trick, one very important practice in field theory. Okay, it's always throw away the boundary term. If it cannot be thrown away, we just choose a different boundary. We can choose a larger area. Okay, so that's the two comments I want to give. So this is the so-called U1 charge conservation law. Sorry, the charge conservation law from gauge symmetry. And the second example we are going to discuss here is the translation symmetry. Okay, and here more precisely we'll consider translation symmetry in both space and time. Okay, translation in space means I will change my coordinates and shift everything by a constant. The translation in space. Translation in time means I will change the origin of my time and shift my time by a constant. Okay, and the reason we want to group translation in space and time together is because in special relativity, we learned that space and time are coupled together through the Lorentz boost. Okay, position and time combined together as a 4D vector. That's our 4-dimensional coordinates. Okay, so that's why we want to combine them together. Okay, so in this section, we will consider translation in space or translation in time. Okay, and again, we will use a 4D formula. Okay, so we can define 4D coordinates are nu. Okay, when nu is 0 is time, or more precisely, when nu is 0, r0 is ct, speed of light times time. Okay, and when nu is 1, 2, or 3, it's space, it's x, y, z. Okay, And then we can define a 4D translation. Okay. I shift this 4D coordinate by constant delta. Okay. And this delta is another 4D vector. That's the translation in my 4D space. And the zeros component of delta gives me time translation in time. And the 1, 2, 3 component of delta gives me translation in space. Okay. So this is a unified translation, and it combines both time and space translation together as one 4D translation. And this is our transformation, the transformation we're going to look at. Okay. And this transformation, again, is a continuous transformation. It's not a discretized one. Okay. Delta is a continuous variable. You can tune it to be very, very small. You can tune it to be very, very large, and you can smoothly change the value of delta from 0. Okay, so that is a continuous transformation. And if the system stays invariant when we do this translation, if my actions stay invariant, if we perform this translation, then we say the system has the so-called translation symmetry. Okay, it has translation symmetry in space and time. And that is the space-time translation symmetry we're going to discuss. And we are going to look at if a system has this space and time translation symmetry, what will happen? Okay, that is our main focus of this section. And another thing I want to highlight is that in this section, instead of E and M field, we will look at a generic setup. Okay, we will look at some general field phi. Okay, so I assume I have action, and this is action of some general field. Okay, this field phi could represent scalar potential, vector potential. It could represent quantum wave functions, elastic wave functions, or anything, some continuous wave function, a continuous part, continuous quantity as a function of space-time points. Okay, and we will look at this most generic setup, and later we will transform and apply this generic setup to E and M fields in our lecture. And in your homework, you will apply this generic formula to some other fields and some other ways, similar to what you did in your previous homework. Okay, so nevertheless, let's assume I have some fields, which we call it phi. This phi can be anything, okay? And I can write down my action. The action is a function of phi and also derivative of phi, as we explained earlier. Okay? And we want to assume the system has translational symmetry in space and time, which means if I do experiment here or experiment there, I get the same result. That's the translation symmetry in space. Translational symmetry in time means I do the experiment today, or I do the experiment tomorrow, I get exactly the same result. That's the translation in time, translation symmetry in time. Okay? So we'll assume this action stay invariant under space-time translation. Okay? And let me massage this formula a little bit. Okay, so we know that the action is the space-time integral of Lagrangian density. Okay? Lagrangian density depends on phi and the derivative of phi. Okay? We didn't emphasize this, but Lagrangian density also depends on the location. Okay? So Lagrangian density is Lagrangian density at this point. Okay? Of course, it depends on which point we are talking about. Okay? So Lagrangian density depends on the point. So I have Lagrangian density at this point, and I have Lagrangian density at the other point, and I do an integral of Lagrangian density. I get Lagrangian action. Okay? So Lagrangian density depends on my space-time coordinates. It depends on field, of course, as we learned earlier. It depends on the derivative of field. Okay, so derivative of field in a 4D space, it includes time and three time derivative and XYZ derivative, 4 derivative together. Let me write this 4 derivative together as partial nu phi. Okay, I will use partial nu to represent all these 4 derivatives. Nu equals 1, 0, 1, 2, 3. Okay. And the coordinate is also a 4D coordinate. Okay, it has 0 coordinate is time, and XYZ has 1, 2, 3 coordinate. Okay, so I will use R nu to represent time and the spatial coordinate of this Lagrangian density. Okay, you may notice that I use the nu and the mu, 2 different index here. This is because these are 2 different vectors. Okay, the time direction of R and the derivative, they are not the same thing. So I use nu and mu to distinguish them. These are 2 different 4D vectors. Okay, and another thing I need to highlight here is what is partial mu? Okay, partial mu is a 4-dimensional derivative. Okay, In the earlier lectures, we showed two different definitions of four-dimensional derivative. One of them is a so-called control variant 4D derivative. That's 1 over c partial t minus partial x minus partial y minus partial z. And we also mentioned another 4D derivative, which is a so-called covariant 4D derivative. It's almost the same thing, but the spatial derivatives don't have the minus sign in front. Okay. Most of the time in the earlier lecture, we are using this one. We are doing the control variant 4D derivative. Okay. The reason we mostly use this one is because this one transforms the same way as 4D coordinates. For example, we do Lorentz boost. This guy also follows the same Lorentz boost matrix. Okay. So most of the time we are doing this one. The other one, this one, it's also a 4D. It's also kind of 4D vector, but it follows the inverse Lorentz boost. If we perform Lorentz boost to the coordinate, this guy behaves exactly opposite to the coordinate. That's why we call them covariant instead of the control variant. Covariant means this guy follows inverse Lorentz boost, exactly opposite to the 4D coordinates. Okay. So in earlier lectures, mostly we are doing this for my derivatives. In this section, let me follow a slightly different convention. Okay. In this section, I will use partial mu to represent this guy, the covariant derivative. Okay. In other words, my partial 1 is partial x with no minus sign. I'm following this convention. Okay. This convention is a little bit different from what we are doing earlier on. Okay. Earlier on, we have the minus sign. Okay. But for the discussion of this section, this convention makes things slightly more convenient. Okay. So that is worthwhile to highlight. So partial 1 is partial x, not minus partial x. In most earlier lectures, partial 1 is minus partial x, but in this section, it's partial x. Okay, anyway, so this is a convention I want to highlight. Okay, and now let's look at this 3 objects. Okay. And how does this object change under translation? Okay. So how does the coordinate change under translation? Well, that answer is easy. Under translation, the coordinate just becomes r plus epsilon. Epsilon is, I'm considering a small translation. Okay, epsilon is my small translation. Okay, so epsilon is my translation vector. Okay, so the first object, coordinate, under translation, it should become this. Very easy. Okay, now let's look at the field phi. How does field phi change under translation? Okay, so let me draw a picture. Let me draw a 1D example. Suppose this is my function phi and the function of r. Okay, so instead r should be a 4D space, but let me only draw one direction as an example. So this is my function before translation, and now I'm doing a translation, translated by a vector epsilon. Okay, after the translation, let me use a different color. Okay. After the translation, the function becomes this. Okay. This is my phi prime r. Right. And this is my phi r. Okay. So the blue one is my my function before I do the translation. The red one is what I did after the translation. Okay. And obviously, we can prove immediately this relation. Okay. My new function phi prime and r plus epsilon. Okay. And r plus epsilon. Say this is my point r. And this is my point r plus epsilon. My new function at point r plus epsilon, its value, should equal to my old function at r. Okay. So suppose this dashed line represents my position r. After translation, r is moved to r plus epsilon to here. Okay. So my function is also moved, which means after I move my function, the red function r prime and this point, its value, should be the same as the function before I move and r. Okay, so that's a definition of how do I shift a function. Okay. So under translation, my function changes following this relation. Okay, that's the same relation we highlighted. Okay, but that is not exactly what we want. Okay? what we want to look at is the change of phi at the same spot. Okay? I don't care about, at the new point, what does this function look like? I want to understand the change of phi at the same spot. Okay? If I look at the same spatial point, same point R, okay, before transformation, the value of the function is phi R at this point. Okay? After I translate the function, after I translate my space, I become red color, okay? And this red colored point, this red colored function at the same point, its value is the same as the blue function at R minus epsilon. Okay? So after translation, if we look at the same space-time point, this function becomes phi prime, okay? And the phi prime at the same point is actually phi at R minus epsilon, okay? So, this is a definition of convention. It's a little bit tricky, okay? So we move the functions this way, okay? So if I look at the same point, if I don't shift my point, if I look at the same point, when I move the functions this way to plus epsilon, the function at this point is changed to the function value at R minus epsilon, changed to this one. Okay, so that's this equation I try to highlight. Okay, so logic here is a little bit tricky. It's a little bit hard to follow immediately. But if you carefully think about this, this is exactly what happened. Okay, if I move my function to this way, and I look at the same point, then the value at this point actually decreases. And how much it decreases? It decreases to the point R minus epsilon. This is R minus epsilon. Okay. So the value becomes the value at R minus epsilon. So after the translation, my function phi at the same point, its value changes from phi at R to phi at R minus epsilon. Changes from this value to this value if I shift the function. Okay, so that's this relation. The bottom line, after I do space translation, if I look at the same space-time point, the value of my function, the value of my field, become R minus epsilon. Okay. If epsilon is small, we can write R minus epsilon as a Taylor extension and ignore higher order terms and only keep the leading order term. Okay. In other words, after translation, if you look at the same space-time point, my function actually changes to my old function minus spatial derivative times how much I shift my space. Okay, so there is a minus sign. That minus sign comes from this minus sign, and this minus sign is very important. This is how field phi changes. Okay? And in addition to field phi, we also need to know what derivative of phi changes. Okay? So this is how field phi changes. Oh, but by the way, before we go to derivative, let me define another thing. Okay, we can define the difference between these two quantities, phi prime and phi, as delta phi. Okay? So delta phi measures that at the same location. I don't change my location. Okay? At the same location. After and before the translation, what is the difference? Okay, so how much does my field change after and before translation? And their difference is what I call delta phi. Okay? And from this relation, we can immediately write down delta phi is just this term, minus gradient of phi times epsilon. Epsilon is how long I translate. And I assume epsilon is small because I'm looking at the small translation. Okay, so that is a change of field. Okay, so the change of field is this guy. Okay. If I do the translation and look at the same point, the wave function, the function phi changes by this amount at the same point, at same spot. Okay. Okay, so this is another way to write down the same thing. My new wave function and my old wave function differs by delta phi, and delta is what we define here for the same space-time point. Okay. And similarly, we can look at the derivative of phi. Okay. So for the derivative of phi, we can use exactly the same formula here. Just take a spatial derivative on both sides of the equation. Okay. If we take a space derivative on both sides of the equation, we find that under translation, if we look at again the same space point, the gradient of phi becomes gradient of phi prime, and gradient of phi prime is old gradient of phi plus gradient of delta phi. Okay, so phi changes to phi plus delta, gradient of phi changes to gradient of phi plus gradient delta. That's the definition. If I add a delta, then the gradient of phi we should add gradient of delta. That's the definition of gradient. Okay, now we know how gradient of phi changes, how phi changes, and how R changes under space translation. Then we can just perform our, we can just look at the new Lagrangian or new action. The new action is again space-time integral. Space-time integral doesn't change under translation. Okay? And then this Lagrangian used to be a function of R, phi, and gradient phi. Now it becomes a function of R prime, phi prime, and gradient of phi prime after I do the translation. Okay? And what is R prime? As we just showed here, R prime is R plus epsilon. That's the definition of translation. Okay? R prime is R plus epsilon. What is phi prime? Phi prime is phi plus delta phi, as we just showed. And delta phi is this guy, gradient of phi times epsilon. Okay. So phi prime is phi plus delta phi. Okay. What about gradient of phi prime? Gradient of phi prime is this formula. Gradient of phi prime is gradient of phi. Oh, sorry, there should be no prime here. This prime should be removed. Sorry, this is a typo. It's gradient of phi plus gradient delta phi. Okay. So gradient of phi prime is gradient of phi plus gradient delta phi. So this is my new action after translation. Okay. Okay. So this is so for every single term, let me copy it again here. Okay. So this formula is right. After I corrected here, this prime should not be there. No prime. Okay. Okay. So this is my Lagrangian after I do a translation in space or time. Okay. So this is my new Lagrangian, and epsilon is a small quantity. We assume it's a small translation. Okay. If epsilon is small, delta phi will be small. Gradient of delta phi will also be small because delta phi and gradient of delta phi both are proportional to epsilon. If epsilon is small, they are small. If these guys are small, we can do a Taylor expansion. Okay? This is Taylor expansion for small epsilon, small delta phi, small gradient of phi. Okay? We have zeroth order term, we have linear term, and we have high order terms. High order terms we will ignore because we are assuming this is a small deformation. Okay? So the high order term we will ignore. The zeroth order term, what is the zeroth order term? Zeroth order term is a Lagrangian density before the translation. Okay? So zeroth order term is exactly what we had before the translation. Okay? So the space integral of zeroth order term gives me an action without prime. This is action before the translation. Okay? And in addition, we have this term, this big beast here. Okay? And this term is actually, let me copy it. It's this term. Okay. And if we want the system to have translation symmetry, if the system has translation symmetry, it means that S prime should be equal to S, which means this whole thing needs to be zero. If the system has translation symmetry, S should not change under translation. So this whole thing needs to be zero. Okay. So this whole thing needs to be zero. And then let me go one step further. We know delta phi. We know what delta phi is. Delta phi is here. It's minus gradient of phi times epsilon. Okay. We plug in the definition of delta phi into the formula. Replace delta phi with this guy and the minus sign. Okay. Now it means that this guy needs to be zero if I want to preserve translation symmetry. Translation symmetry means this one is zero. Okay. And it's actually okay. Actually, this one needs to be zero. And here again, we play the trick of integral by parts. Okay. Oh, sorry. Before we play before we play the trick of integral by parts, we need to do one more thing. Okay. That's one more thing we need to do is we use actually the equation of motion. Okay. So actually, what I did here is I put the common factor epsilon. I put the common factor epsilon outside my parentheses. Okay, I put it out. Okay. So now let's utilize the equation of motion. So this is the equation of motion we learned from the previous lecture. Okay, if it requires a variation of action to be zero, the variation of Lagrangian density to phi should equal to the partial mu variation of Lagrangian density to partial mu phi. That's the equation of motion we showed earlier. Okay. And if we use this formula, we can replace this term by this guy. Okay. This term is exactly the left-hand side of the equation of motion. It should be equal to the right-hand side. I replace this guy with this guy. And then my second term changes into this. Okay. Okay, once we do that, we realize immediately these last two terms can be combined together as one derivative. Okay, here we use the trick. Oops. Partial mu function f times g plus f partial mu g equals partial mu f times g. Okay, that is what I use. So we can combine these two terms together as one derivative. Okay, so that's what we did for the last two terms. And for the first two terms, we will play a small trick. Okay, the small trick is I want to change this partial mu to partial mu. The reason I want to change it to partial mu is because the second term has partial mu. I want them to be the same derivative. Okay, how do I change partial mu to partial mu? Well, I use chronic delta. Chronic delta delta mu mu says if mu equals to mu, it's 1. If mu not equals to mu, it's 0. Okay, by multiplying a chronic delta, this partial mu times chronic delta is partial mu. This is just a trick. After this trick, I have partial mu here. I have another partial mu here. So I can pull the common derivative out. So it's a partial mu of the two terms combined together. Okay, so this term needs to equal 0 to preserve the translational symmetry. Okay. Let me multiply -1 on both sides. For historical reasons, people choose to do that. Okay. If we multiply a -1 to that, this term becomes here, and the L term becomes a -L term here. I switch these two terms by multiplying -1 on both sides. Okay. And this side, this quantity should equal 0 because of transfer symmetry for any epsilon, for any epsilon. If we want this quantity to be 0 for any epsilon, then this thing inside the square parentheses need to be 0, and this thing need to be 0, and this guy is a continuity equation. Okay, this guy is a continuity equation, and we will demonstrate this more carefully in the next part. Okay, to understand that this equation is the continuity equation, let's first look at the time translation. Okay, so for the time translation, it's governed by exactly the same equation. So we have exactly the same formula here. Okay, so let me erase the drawings to get some space here. I'll erase everything. Okay, so for the time translation, we have exactly the same formula, except that now the translation is only along the time direction. Okay, if the translation is only along time direction is our 0 direction. So the zeros component, I have delta t, that's my time translation. And xyz direction, I don't do any translation. Okay, so if I only have the time component, then in other words, I only have 0 components for my equation, and this is what I got. Okay, I got epsilon 0 here, which means this index should be 0, and this derivative should be 0. Okay, this derivative is the same index as epsilon, so this derivative should be 0. Okay, so if we do a time direction translation, this is the equation we get, and this guy should equal 0. And in other words, this whole thing is a square bracket should be 0 for time translation. Okay, so for time translation, this is 0, this is delta mu 0, and this is the equation we get. Okay, let's look at this equation. We know that partial mu means a derivative, and for mu, we need to include the derivative of both 0, 1, 2, 3, or 0, 1, 2, 3. Okay, so this formula, we have a repeating index mu and mu, which means I need to set both of them equal 0, both of them equals 1, both of them equal to 3, both of them equal to 3, and sum them together. This is Einstein's convention. Okay, with repeating indices, we sum over it. Sum over 0, 1, 2, 3. Okay, and the partial zero, as we have shown earlier on, partial 0 is 1 over c partial t. So this partial 0, I should replace it on 1 over c partial t. I should do the same thing for this partial 0 and this partial 0. Okay, so for this two partial 0, their 1 over c coefficient cancel because 1 is denominator as numerator, so they both become partial t. Speed of light cancels out. Okay, for the second term, partial 1 is partial x according to the convention we discussed earlier on. Okay, so in the earlier part of the lecture, most of the time we set partial 1 to be minus partial x. As I explained earlier on in this section, our partial 1 is just partial x. This is the convention we utilized. Okay, so partial 1 is just partial x, and I also need to replace this partial 1 by partial x. Okay, I have partial 0 here. I should replace this partial 0 by partial t, but also with 1/c factor. That 1/c factor, put it in front. Okay. We do the same for partial 3 and partial 2 and partial 3. Okay. So this 1/c comes from this partial 0. This partial 0 gives me this 1/c. Same is true for all the other two terms. Okay. So every single term has 1/speed of light. Let me cancel 1/speed of light. Okay, cancel all of them. So I have this 4 terms added up together to 0. Okay, that's what we get from translational symmetry in time. And this translational symmetry in time, this equation, let me define some quantity. Okay, let me call this quantity, the quantity in the first parenthesis, to be my W. Okay, I call it W. Okay, this is just whatever we have here. And there are two ways to write it. We can write it as partial t or partial 0, and they're the same. Okay, partial t and the partial 0 are pretty much the same. You differ by speed of light, and the speed of light perfectly cancelled. Okay, and I call this guy in the second parenthesis Sx. Okay, and I call this guy in the third parenthesis Sy. This guy in the last parenthesis Sz. Okay, I just give this 3 parentheses a name. Then my equation immediately becomes this guy. Okay, partial t of W, this is W, partial x, partial y, partial z, partial x, partial y, partial z, Sx, Sy, Sc, Sx, Sy, Sc. Okay, and let me define Sxy, Sx, Sy, Sz together as a vector S. Okay, 3D vector S. If I define this 3 quantity as a vector 3D vector S, then I can rewrite the last 3 terms as the divergence of S. Okay, so this divergence of S is exactly this form. And now if we look at this equation is exactly the same continuity equation. It's exactly the same as continuity equation. Okay, charge density now becomes W, and current density now becomes this S. Okay, so again, so same as the charge conservation law, here we get a continuity equation. As we explained earlier on, continuity equation in continuum system is a charge is a conservation law. Okay, the conserved quantity is this guy. Okay. So this W is a conserved quantity density, is the density of a conserved quantity. This is same as the charge conservation law. This rho is the charge density. Okay. If we do the integral, spatial integral for this density, we get a number. That number is our conserved quantity. Just like if we do a spatial integral for rho, we get charge, and charge is our conserved quantity. Okay. And this vector S is the current density for this conserved quantity. It measures how fast this quantity flows in real space. It's just like charge current. Okay. So for charge, the charge current J measures how fast the charge flows in our system. Here is the S, measure how fast this conserved quantity flow in our system. Okay, so the integral of rho in real space gives me the conserved quantity charge. Here the integral of this W in real space also gives me a conserved quantity. And this conserved quantity is a conserved quantity comes from the time translation. In classical mechanics, we learned that the time translation symmetry, if something is translational environment in time, it means there is a conserved quantity, the energy is conserved. Okay. Energy conservation is associated with translation symmetry in time. Okay. So this conserved quantity, in fact, is exactly energy. So this conserved quantity is nothing but energy. In other words, W is energy density. It measures that how much energy I have per volume and around this point. Okay. If I have energy density to be W and then I integrate over a region, then I get the total energy inside this region. And this vector S is energy current density. Okay. So this is very similar to charge. Okay, so for charge, in continuum, we define charge density, okay, and the charge density, and we define current density. And for energy, if we have a continuum medium, energy distributed continuously in real space, we need to define an energy density and the energy current density. Okay, so let's look at charge as a comparison. Okay, so for the case of charge, we know that this is continuity equation. Okay, then we know that we can do a spatial integral on both sides for both terms. It should still be 0. Okay, the spatial integral of rho in the first term is Q, is my charge. inside this volume omega. Okay, so the first term becomes partial Q partial T after we do the spatial integral. The second term is a spatial integral of a divergence of J. Okay, spatial integral of divergence of J, we can use Stokes' theorem to convert this term into a surface integral. Okay, so this second term is actually a surface integral. The first term measures how many charge we have inside system, inside this volume omega. And the second term is the current that flow out of the system. Okay. The current density tells me every single point what is the current per area. If I integrate over the whole surface, then this is total current that flow out of the system. My charge conservation law tells me that the charge, the time derivative of charge inside system should depend on the total current that flows through the surface. That's a charge conservation. Okay. And for our W and S, it's exactly the same story. The integral of W inside omega tells me the total energy inside this region. Okay, and the delta, that's the dot product of S, divergence of S, if we do a 3D integral, then again we can use Stokes' theorem to convert this into a surface integral. Okay. And this surface integral measures the flow, the current of energy that flow out of the system through the surface. And energy conservation law tells me if my energy is changing inside this area, then there must be some energy flow through the surface. That's described by this term. Okay. So this is energy conservation. Okay. Let me summarize. If we look at translational symmetry in time, our equation we find becomes this guy, and that is a continuity equation. It defines as the energy density and defines as the energy current density. That's the most important thing from the translational symmetry. Okay. Okay, so the energy density and energy current density follow exactly the same story. Okay, so this technique does not actually only tell us translational symmetry in time gives me energy conservation law. It also gives you the specific definition of energy. Okay, we know that energy density must be this one, which means as long as we know the action or we know the Lagrangian density, we can immediately use this formula to write down what energy is. What is energy? What is energy carried by this wave? What is energy carried by this field? No matter this field is electric magnetic field or elastic waves or quantum waves, Schrödinger equations, no matter what it is, as long as we know the action and the Lagrangian, we can use this formula, immediately define energy density. And then if we do a spatial integral, we get the definition of energy. That's the definition of energy. So this not only gives us a symmetry, a conservation law, it also tells us what is energy, how to write down energy. And it also tell us immediately how to write down the current of energy. Okay? As long as you know Lagrangian, immediately we can write down the formula to measure how fast energy flow. That's the energy current density. Okay? So this is the energy conservation. Okay. So in my lecture notes, actually I posed the question: how do we know this is energy conservation law? Okay. The first reason we just discussed, because we know translation symmetry is related to the energy conservation. And this is a conservation law from time translation, so it should be energy conservation. There is another way to understand that this is energy conservation. That is by looking at this formula. Okay? If we look at this formula, this is energy density, the same formula we got about here. Okay, so energy density W equals this. If we look at this formula long enough and go back to our earlier lectures, you will realize this formula is exactly the same formula as what we write down for Hamiltonian. Okay. Last week, we showed that if we have Lagrangian, we can use a round transformation to get Hamiltonian. That's exactly this formula. Okay. Delta L, delta partial T phi is the canonical momentum, Momentum times partial T phi minus Lagrangian density is exactly what we use to define Hamiltonian density. And we know Hamiltonian density, Hamiltonian is related to energy. So this is Hamiltonian density, so this must be energy density. So this is another way to understand this is indeed the energy conservation law, and the W is indeed the energy. Okay. Okay, so the bottom line, for any field theory, as long as the system has translational symmetry in time, which means we do the experiment right now and we do the experiment tomorrow, we get exactly the same answer, then we will get immediately the conservation law. That conservation law is written in terms of continuity equation. We can get the energy density and energy current density, and this is the continuity equation for energy conservation. Okay. The energy density is immediately, can be immediately written down, as long as we know the action Lagrangian. Okay, and the energy current density can also be immediately written down, as soon as we know the energy. Okay. And one more comment I want to make before we conclude this energy conservation law, that is, in the previous part of this section, I'm assuming there is one field phi in our system, right? But in reality, my system may contain multiple fields. For example, in E and M, I have 4 fields: scalar potential and 3 vector potential, AX, AY, AZ, not only one. Okay? If we have multiple fields, we can go through exactly the same calculation and get exactly the same formula. Okay? Okay, so this is for one field. If you have multiple fields, say phi 1, phi 2, phi 3, the subindex represent different fields, then we can do this same structure for each phi, for phi alpha. Okay, we replace this phi with phi alpha, replace the denominator with phi alpha. Different alpha represent different fields. Okay, and notice that the denominator alpha and the numerator alpha are the same. They have the same index here, and we sum over alpha. Okay, so we replace the first term by this guy, sum over all fields. And second term minus Lagrangian density remains the same. Okay. And this sum over alpha, we can use the Einstein convention. Using Einstein convention, it says that we have a repeating index, alpha appears twice. So alpha will be automatically summed over. So we don't really need to write down the sum over alpha if we use Einstein's convention. Okay. So the energy density with multiple fields becomes this. Okay. And the energy current density with multiple fields becomes this. Okay, so previously we only have one field phi. Now we have multiple fields, phi alpha. Okay, and alpha goes from 1 to some numbers n. Okay, and we do the same thing and we sum over alpha. And again, using Einstein convention, I don't really need to write down the sum over alpha because alpha is a repeating index. It should automatically be summed over according to Einstein's convention. Okay, so the bottom line, no matter how complicated your action is, no matter how many fields it contains, we can use the same formula here. Just remember we need to do the same for every single field and add them together. That's the total energy density and the total energy current density. Okay, so this is a formula for multiple fields. This is a generic formula. And later in next lecture, we will apply this formula to E and M fields, where alpha is 0, 1, 2, 3. 0 is scalar potential, 1, 2, 3 are the vector potentials. Okay, so this is the energy conservation. We can do exactly the same thing for space translation. Okay, so for space translation, say space translation along x, this time the epsilon vector is 0 for the time component. I'm not changing time. I'm shifting x by a small amount, epsilon x, and I'm not shifting along y and z. So the yz component is 0. Okay, then again we have the same formula. The epsilon mu here is 0, epsilon x 0, 0. Okay, so I only need the x component. X component is my component 1. Okay, so I have 0, 1, 2, 3. X is 1. Okay, so I only have the component 1 in this equation. Okay, so I only keep the component 1 here, which means this is the delta mu 1, and this is partial 1 phi. Okay, because my epsilon is only 1. Epsilon 2, 3, and epsilon 0 are all 0. Okay, so if we do translation along x, the translation symmetry tells me this object is 0, which means again this object in the square parentheses, square bracket need to be 0. Okay. And this guy in the square bracket need to be 0. Again, we have the mu and the mu. We have repeating index. According to Einstein's convention, we should sum over mu. So mu both being 0, mu both being 1, mu both being 2, mu both being 3, and we sum over all of them. Okay, we sum over this. And again, we replace partial 0 with 1 over c partial t. Partial 1, partial 2, partial 3 are just partial x, partial y, partial z. Okay, we do the same construction as what we did in the previous section. Okay, then we got this formula. Again, I give every single object inside this parenthesis a name. The first guy, I call it the gx. Okay, the second guy, I call it the txx. This guy, I call it the tyx. This guy, I call it tzx. Okay, we just gave each of these terms a name. Once I give each of terms a name, the same equation now can be written in a much compact formula, that is partial t gx equals partial xt, partial yt, partial zt. Okay, and again, I can combine these three t together. Okay, txx, tyx, tzx together as a three-component 3D vector. Okay, I will call that vector t. Okay, and that vector, then this term becomes a divergence of t. Again, the time derivative of a quantity plus divergence of quantity equals 0. That again is a continuity equation. Okay, so translation along x define again for us a continuity equation. And the same as before, gx, the one related with time derivative, is my conserved current, the conserved density. Okay, so gx is the density of my conserved quantity. Okay, so gx is density of conserved quantity. And the spatial integral of gx in some volume omega is my conserved quantity. And this conserved quantity is nothing but the x component of momentum. This is px. Okay. We know that from classical mechanics, translational symmetry is related with momentum conservation. Okay, and we are doing translation along x, so the conserved quantity we get, it's the x component of the momentum. Okay, so this g integral in some volume is x component of momentum. In other words, gx is the density of momentum, also known as a momentum density. Okay, so gx is my momentum density. And the txx, tyx, tzx describe the flow of momentum. It's the current density of momentum. Okay. And we can repeat the same procedure for translation along y and translation along z. If we do that, we get similar, we get exactly the same structure, exactly the same conservation. We get a gy, gz. Okay, so gy is a momentum density for the y component of momentum. Okay, it's very similar to gx, except that the partial x now becomes partial y. Okay, gz is the z component of the momentum. Okay, more precisely, the momentum density for the z component of the momentum. Okay, and we can combine gx, gy, gz together as a 3D vector. And that means this derivative, partial x, partial y, partial z, we combine them together as a 3D gradient. Okay, gradient is vector, so vector equals vector, 3D vector equals 3D vector. This is the momentum density for a continuous system. Okay, and if we integrate this momentum density over some region, we get our conserved quantity, which is momentum. Okay, so translational symmetry. Again, we find that translational symmetry in space also gave us a conserved quantity. And actually, it's not one conserved quantity, it's three conserved quantities, one for x, one for y, and one for z. And these three conserved quantities together forms a 3D vector, and this vector is just what we call momentum in mechanics. Okay? And again, once we know the Lagrangian, we can do this calculation and immediately figure out what is the formula for momentum. Okay? And again, this formula can be applied to any fields, any continuum fields, including EMM field and also quantum mechanics, Schrodinger waves. Okay, so this is the momentum. And for the y and z components, we can also we can define three conserved three current density. Okay, so for the x component, we got 3 t's. For the y and z component, we each get 3 t's. So we can combine this 9 t's together to form a 2x2 matrix. This matrix, actually, if we write down the formula, it's look like this. And this is actually the rank 2 tensor, 3D space rank 2 tensor. This rank 2 tensor is what the people usually call momentum current density tensor. Okay? So momentum is a vector. The current of momentum is actually a tensor. This is actually very similar to charge and energy. For charge and energy, the conserved quantity is a scalar. And as a result, their current is a vector. Okay, so this is a rank 0 tensor. Scalar is also called a rank 0 tensor. And their current is a rank 1 tensor. Rank 1 tensor means it's a vector. Okay, but if your conserved quantity is, say, momentum or momentum density or G or P, okay, your conserved quantity now is a vector. And the current of a vector is T. It's a rank 2 tensor. Okay, so the current always has one more rank than the conserved quantity itself. When the conserved quantity is a scalar, the current is a vector. So that's why current density for charge is a vector. That's why current density for energy is a vector. But for momentum, the story is different. Momentum is already a rank 1 tensor. So the current should go 1 rank higher, so it's a rank 2 tensor. The current density of momentum is not a vector. It's actually a 3 by 3 matrix. It's a rank 2 tensor. With this vector momentum density G and the tensor momentum current density T, we can write down the continuity equation in this way. Oh, sorry, there is a typo here. This should be partial T G. I missed the partial T. I will add this before I post the lecture notes. Time derivative of the momentum density plus the spatial gradient for T Ji, and this derivative is along the same direction as the first index of T equals 0. Okay, so this is my continuity equation. And this continuity equation can also be written in this way. Okay, well, we know G is a vector. Okay, and the derivative, spatial derivative is a vector. Okay, the first term is time derivative for a vector, and the second term is the derivative vector times the 2 by 2 matrix. And 3 by 3 matrix. And derivative vector times the 3 by 3 matrix gives you a 3D vector. That 3D vector add with this 3D vector equals 0. That's a continuity equation for momentum. This continuity equation is slightly more complicated than the energy and the charge, because energy and charge are scalar. But this conservation law here is momentum, and momentum is a vector. Okay. Okay. So that is momentum conservation law. Or we can also write down the momentum conservation law in this way. The first equation is the x component of the momentum conservation law, the x component of this continuity equation. That gives me the energy, momentum conservation law for momentum x component momentum. The second one is the conservation law for the y component momentum. The last equation is a momentum conservation law for the z component of the momentum. Okay, and finally, let me generalize the formula for multiple fields. If our Lagrangian contains multiple fields, phi 1, phi 2, phi 3, lots of phis, then for each phi, we should do the same construction, and we add them together. Okay, for every single phi alpha, we do the same combination, and we add them together. And if we use Einstein's convention, we don't need to write down the sum over alpha, because we automatically sum over alpha. So we can also write a formula like this. Okay. And for the momentum current density, T, if we have more than one field, again, we use the same structure. Again, we should do the same construction for all fields, every single phi alpha, and sum over alpha. Okay. And again, we can use Einstein's convention to write it into a more compact formula, which is this. Okay, so this is momentum conservation law.